very pleased to introduce today William Oliver, who came to visit us from MIT Lincoln Labs. He's also an adjunct professor at MIT, and Will works in superconducting qubits and essentially covers the whole hardware stack, if you want to call it such, from fabrication to design of superconducting qubits to measurement, all the way to the control electronics. In fact, Will is regarded as one of the up-and-coming stars in the area of superconducting designs. Will has a very eclectic bio so far, as I saw. For example, he worked for 2 years on an interactive music installation, which I think 2 weeks before Burning Man starts is maybe an appropriate topic to talk about. But on the more serious side, in 2003, he got his PhD in electrical engineering from Stanford. He had a Master of Science in electrical engineering and computer science, 1997, from MIT. And he even has a bachelor in Japanese from Rochester University. And yeah, we are very glad to have you here and hear sort of about the latest designs that are going on at Lincoln Labs. Lincoln Labs has, from our perspective, a very interested IARPA-funded program on quantum-enhanced optimization, which is pursuing very similar goals to ours, to use quantum resources to solve hard optimization problems faster than any classical machine could. And we'll report a little bit on this.
Okay. Well, thank you very much for that introduction, Hartmut. I'm really pleased to be here today to be able to talk with you about the work that's going on both at MIT Lincoln Laboratory and also MIT campus. And so I framed this talk under the general title, as you can see, Quantum Engineering of Superconducting Qubits. It'll be mostly a high-level talk. I'll include a few recent results, but mostly I just want to give an overview of the breadth of the work that we're doing. And before I get started, let me acknowledge team and collaborators both at Lincoln Laboratory on the left, as well as the MIT campus on the right. We also collaborate with a group in Japan, Yasunobu Nakamura, and also a group at UC Berkeley, Irfan Siddiqui and John Clark. So by way of introduction, if we consider a timeline of computing, we could say that there was a first information processing revolution that happened in the 20th century. And this started with the vacuum tube, really, which was invented in 1907. It was about 40 years later that we finally had the ENIAC, one of the first tube-based computers. Of course, contemporary with that, the transistor was invented, and it took not too long to have the first transistor-based computer, but to get to something that looks like what we're using today, it was really several decades as well, and on and on. On the quantum computing side, it's a much newer story. Richard Feynman in the early 80s suggested that we could build a very powerful machine if we build it based on the rules of quantum mechanics. And so this was an idea that got kicked around for about a decade, and a real punch came with Peter Shor. And two things that he did in 1994. The first is that he came up with Shor's algorithm, which we'll talk about in a moment, the first real practical quantum algorithm that had a real application. And the second thing that he came up with was a way to allow a fault-tolerant quantum computer, so essentially quantum error correction. And so, okay, then the US government gets involved and starts funding people, and sure enough, a decade or so later, we're starting to have the first milestones in these qubits or fundamental elements. And I think that many of us believe that quantum information will lead to a second information processing revolution. And it's not just us, of course, there's worldwide investment here, and I just show a few of the places around the world, and I'm sure that I've missed a few, that are investing in this area. And of course, within the last couple years, we've even seen companies jumping in, including, of course, Google, Microsoft, Intel's thinking, and IBM's also involved. And the reason that people are getting involved now is because it's becoming real, and we're at a stage when we can do engineering of these devices, and the potential value for economic and as well as information security is driving this investment. And so Peter Shor, as I mentioned just a moment ago, came up with this algorithm for code breaking or factoring. As you know, public key encryption is based on RSA. It's a one-way problem. It's difficult to factor a large number into its primes, a composite, but it's easy to multiply those two together and confirm that you, in fact, were successful. And known classical methods require exponential resources to do this. If you're dissatisfied with the level of security, double the, the length of your encryption key, and it will get exponentially harder. Now, what Peter Shor showed is that with a quantum computer, you can actually do this in an efficient amount of time. And the plot here, okay, assumes a lot of things, but if you take a petaops computer and you ask, what's the computation time in hours for a bit length key, it gets to be, extraordinarily long, even the age of the universe by the time you're at 2048 bits. Whereas a quantum computer based on superconductors, let's say, running at 100 megahertz could solve this problem in about an hour. So, okay, for a long time people asked, is that the only application? And the answer is, well, no. In fact, Richard Feynman, when he first talked about this, he said it's actually the simulation of quantum systems that's the most interesting. He said, look, nature's not classical, and so if you want to make a simulation of nature, why not make it quantum mechanical? And in fact, Seth Lloyd at MIT was the first one to show that this could be done efficiently. And so you want to use quantum to simulate quantum. And the applications here include quantum chemistry, materials science. You could even stretch that to optimization problems as well. And so, as I'll show you, I think the past decade in quantum information has really taken these qubits out of the laboratory, and they've developed to a point where we're ready to actually engineer them into larger systems. And so what this graphic is showing is essentially that, we started with transistor tubes and made it, or we started with vacuum tubes and made a vacuum tube computer, and then the transistor came along, and we made those, transistor-based chips, and we certainly adopted a lot of what we had learned in making the vacuum tube computer. Not all of it, but some of it. And we're now at the right side here where we have qubits that are working, and now the question is, we want to build, there's some goal, let's say it's a quantum information processor, and what can we use that we already know to do that? So here's the outline of my talk. I'm going to give a fairly basic introduction to quantum information science and to superconducting qubits. And then I would like to talk about what we're doing at MIT now and Lincoln Laboratory in terms of quantum engineering, both on the qubit plane as well as the control and the readout plane. And so you could ask the question, how is a quantum computer different than a classical computer? So a classical computer we're all familiar with, it's based on a bit, a classical bit. This could be a transistor. And the states are 0 and 1. It's binary. These are discrete, and they're deterministic. If you set it as 1, unless there's some error, you will measure it as 1. If you set it at 0, you'll measure it as 0. A quantum computer, in contrast, is a quantum state. It's a two-level system, but you can have a superposition of states, both 0 and 1 simultaneously. And this superposition is what makes this computer powerful. And one consequence is that measurement is now probabilistic. If you repeat an identically prepared state in a 50-50 superposition over and over again, half of the time you will measure 0, and the other half of the time you will measure 1. And so quantum computers rely on encoding information in fundamentally different ways than their classical counterparts. The consequence of this is that if you have n bits in a classical computer, you have one n-bit state. So if n is 3, then 2 to the n is you have 8 different states. But if you want to process on them all, what you have to do is parallelize, right? So you either repeat the hardware that you use to compute, or you extend in time the computation. Whereas in a quantum computer, you have 2 to the n components simultaneously. And so let me give an example now of how this works. So imagine that you have 3 atoms. You call these qubits. They're two-level systems. They're coupled together. And this gives you 8 possible states. And the state space is listed at the upper right, with coefficients C1 through C8 indicating the various possibilities. The quantum state would be written as such. This notation is called the Braket notation or Dirac notation. And the state requires these 8, in principle, complex numbers, C1 through C8, to specify it. And so we can give an example of what quantum parallelism means in the following way. So imagine that we target just the first qubit on the left, and we apply a pulse to it that will flip the spin. If it's up, it becomes down, and if it's down, it becomes up. So you can think of this as an inverter. And when we apply this pulse, we're actually applying it to the entire state space at the same time. So what that means is that coefficients C1 through C4, which were ascribed to the spin up, they move to now being with the spin down. And C5 through C8 now move from down to up, as you can see. And so by applying one pulse at one time, we're operating on the entire state space. This is an example of quantum parallelism. Now we can do something further, which is quantum interference in these systems, which has no classical counterpart. And the way that we can illustrate that is, imagine now we have another laser beam that targets the third atom and does what we call a pi/2 pulse. And what that means is that if you start with a spin up, that's going to rotate it 90 degrees, thus pi/2, and create a superposition of up plus down. And so if we just look at the first element of this register, the up, up, up spin combination, and the coefficient C5 in front is now spread between the first two elements on the right. And I'm not worried about normalization here for experts in the crowd. Now, instead, if the spin were down, this same rotation rotates it to a superposition of up and down, but it does so with a minus sign, and that's very important. And this is due to quantum mechanics. And so the coefficient C6, as you can see, on the right, adds to the spin up, 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 it adds, and in the next one it subtracts. And so if C5 and C6 happen to have the same amplitude, then the up, up, down state would destructively interfere. And so there would be no more amplitude for that state. This is an example of quantum interference. And in fact, it's also an example of quantum parallelism because it happens on the entire register at the same time. Now, we can extend this further and say, what is a quantum algorithm in the gate-based model? And so what it is that we start with an input state, let's say an equal superposition state shown on the left of all the different states. And the first thing we do are the single qubit operations of the type we just saw, followed by quantum interference. And what that does is it modifies the coefficients in front. So whereas they were an equal superposition to begin with, they now go to alpha, beta, gamma, delta, et cetera. Now, there's another type of operation called coupled qubit operations, where the state of one qubit depends on the state of the other qubit. The operation that it does on qubit 2 will depend on the state of qubit 1. And that is also followed by quantum interference. And the goal of anybody who writes this algorithm is to, of course, solve a problem, but also to do it in such a way that at the end, after many, many applications of these gates, that almost all of the amplitude, or ideally all of the amplitude, is located in one of the states at the end. And that is the state which tells us the answer. Because we know that despite this, this Hilbert space, this 2 to the n massive increase in the state space that a quantum computer affords us, measurement has an exponential decrease, a collapse down to one state. When we make a measurement, we only measure one state. And so it behooves us, when we write an algorithm, to make sure that all of the probability amplitude is in the state that has the answer, so that when we measure it, we get the right answer. OK, so the elements that build up these computers are, of course, qubits. And there's an intuitive figure of merit for the quality of the qubit. I want to note that this is not rigorous, but I think it brings some intuition. And what that is that, first of all, there's a gate time, right? How long did it take me to do this pi pulse or this pi/2 pulse? It's a time required for a single operation. Clearly, faster is desired, right? So classical processors, for example, if they run at a gigahertz, then we're talking roughly a nanosecond clock. And so with 100% activity factor, that's a nanosecond per op. Okay. The second thing about a qubit is that it has a coherence time, and that's the duration of time that it remains quantum mechanical. That's the qubit's lifetime. And so we start with this perfectly quantum mechanical qubit state, but unfortunately, due to its interaction with the environment, it will lose coherence. And you can think of this as the state is becoming blurrier and blurrier over time, and eventually the state is lost. So these are these two time scales. And the one figure of merit is the ratio of these two times. And it's essentially a measure of how many operations can I do before I lose my quantum coherence. And it turns out that you can sustain quantum computing operations by quantum error correction, provided you reach a certain threshold. And that threshold for certain codes, the most lenient ones, is about 10 to the 3. And so now let me say, OK, so that's just the intuitive metric. The real metric is, what is the error per gate that I have? So I think I'm applying a pi pulse. And the question is, how close to that did I get ideally? Was it 100%, or was it not quite 100%. And it turns out that we need to do that, both applying the pulses as well as the readout, with at least 99.5% fidelity. So that means about 0.5% error per operation. And I can say with superconducting qubits, we're there. We're actually beyond that now. And so, well, what are these candidates? I mean, we're talking about superconducting qubits, but there are many candidate two-level systems that we have to our, at our disposal. Why did we choose superconductors? And I should say at Lincoln, we're actually working on both trapped ions and superconductors. So what's plotted here is the figure of merit versus the gate speed. And here's this lowest threshold for achieving quantum error correction. Of course, you want to be as far beyond that as possible, but you need to be at least this good such that adding redundancy makes the computer behave or operate better. The best performance is in the upper right corner. So if we look at trapped ions, they have a gate time that's about 10 to 100 microseconds. Their coherence time is maybe 1 to 50 microseconds, and so you can see where they are placed. And superconducting qubits, they have a gate time of about 10 nanoseconds, coherence times of about 100 microseconds, and that places them there. And so what it means is in the superconducting qubit side, we're continually trying to improve the qubits to give them higher coherence. They're already relatively fast. And the ion trap side, they're already high coherence, but they're relatively slow. And so they're at Lincoln Lab working on ways to make those gate operations and the readout faster and faster. And it matters, right? Because if you have, for example, a quantum computer that's working, you're factoring numbers, great. It doesn't take the age of the universe. It takes my superconducting quantum computer only a day to factor that number. It will take the ion traps about 1,000 days, so 3 years. So the prefactor absolutely matters. It's not just the exponential speed up. So we've talked a lot about this, what we would call gate-based. It's you have a universal set of single and coupled qubit gates, and you can do things such as factoring, quantum simulation. And in this case, for gate-based quantum computer, there's a known speed up over classical means. If we can build this computer, it will work, and it will be much better than what we have today. The other type of computer is called a quantum annealing computer, and this solves things such as traveling salesman problem, essentially optimization problems. And here, there are many, many applications that it could be applied to if it works, but it's unknown if there's a quantum speedup. And that's an active area of research, both I'd say at Lincoln Laboratory and also here at Google, is to try to identify problems for which quantum annealing will give a quantum speedup. So conceptually, what is a quantum annealing algorithm? The idea is that you have a Hamiltonian or a state of the system, and initially this is a known starting point. There's also the problem Hamiltonian, which encodes your problem, and that's encodes the answer. And the goal is through annealing to slowly transition from this known state to this encoded state. And so the way this works is, as it's illustrated, the little red dot is going to tunnel over to a lower energy state. And there are two ways that it can get there. And one is through thermal activation, and the other is through quantum tunneling. And so what quantum computing brings to this problem is a new pathway to get there, and that is through quantum tunneling to find the global ground state. And the extent to which this works will give us the answer. And the real question, the open question is, does quantum tunneling provide a superclassical speedup? And we don't know the answer to that. So if we ask the question, what is the hardware pathway now that we have these qubits to building a quantum computer? Well, step one is, let's make sure we have single and coupled qubit gates for a gate-based model, or in fact for a quantum annealer too, or maybe you want to have a 3-body interaction or 4-body interaction. The next step is to demonstrate that you can control it, so error correcting parity checks, syndrome measurements, high connectivity in the case of an annealer. And then I think where we are now is that we're building initial test beds. So this is between, say, 10, 100, 1,000 qubits, where we can really test either in the gate-based case, logical protection, quantum error correction, sustained operation, or in the case of quantum annealing, let's find problems that can give a quantum speed up. And beyond this is outside the scope of this talk. And it's going to stand on many, many technologies, right? So at the bottom here we have, of course, theory, and we know in theory this works. Physical qubits, we've done 2 to 5 qubit experiments. But where we really need to focus on, I think, in the next decade is architecture and logical qubits. So architecture, of course, is how we lay these out to achieve the most efficient implementation. And logical qubits, in the case of gate-based, is allowing sustained operation. And there's also error correction possible with quantum annealing. And these are clearly engineering directions. So we're talking about fabrication, control electronics, both at room temperature and cold temperature, packaging, on the computer science side, the data path, the compilers, predictions of performance. These are all things that are key, and this next decade is when it will happen. So let me say that we're trying to address all of these things at MIT and Lincoln Lab. This is our group called Quantum Information and Integrated Nanoscience Group. We're focused on superconducting qubits and ion traps on the quantum computing side. But we have a lot of effort on the classical side as well. For example, classical superconducting electronics, CMOS, cryogenic CMOS, 3D integration, integrated photonics. And these really, as you can imagine, all come together to make a quantum computer a reality. So let me move on now to superconducting qubits. And how do we build a superconducting artificial atom? What starts with a linear resonance circuit. So take an inductor and a capacitor, put them together. It has a resonance frequency, as you can see, goes as 1 over square root of LC. And we desire that it be low loss because we want this qubit to live as long as possible. And so to do that, we use superconductivity. So we build these elements out of superconductors, which, as you know, if you take a normal metal with electrons and cool it below a transition temperature, the electrons pair up and form Cooper pairs, and they lose their resistance. They become superconducting. So it's truly resistance equals 0 at DC. Dissipationless, and of course these Cooper pairs are all phase coherent with one another. And what that means is that this LC circuit is actually quantum mechanical. So if we cool it to a low enough temperature to make this thing superconduct, what you'll find is that it's a harmonic oscillator, and it has a discrete set of energy levels, 0, 1, 2, states 0, 1, 2, and 3, and they're each separated by a resonance frequency, nu naught. And this quantized electric harmonic oscillator looks like a quantized electromagnetic field. There's a term which corresponds to the capacitive energy and a term which corresponds to the inductive energy. And in fact, these two variables, charge and phase, or voltage and current, do not commute. They have a commutation relation that's non-zero. It's non-trivial. So they're not simultaneous observables in this quantum domain. So this is okay, but the problem is that these linear elements make a harmonic circuit. And what we would like is a two-level system. And so we're not able to uniquely identify a 0-1 transition without also driving the 1-2 and the 2-3 because they're all degenerate. So what you have to do then is to make a nonlinear element. And for us, it's very easy to do that. It's called the Josephson junction, which is a nonlinear inductor. And essentially, as is illustrated here, there are two pieces of superconducting material separated by a very narrow insulating barrier, about a nanometer. And the phase coherence on one side links up with the phase coherence on the other side. There's a net phase drop across this junction. And the current that's going through this Josephson junction is proportional to the sign of that phase. And the voltage drop across the junction is proportional to the time rate of change of that phase. And so we can define an inductance, clearly L di dt, and as you can imagine, there are lots of nonlinearities here, and this leads to a nonlinear inductance. And so that's exactly what happens. By combining the current and the voltage together, there's a nonlinear inductance. We put that into this LC circuit, and it becomes anharmonic. So as a result, we can address the 0-1 transition independently of the higher levels. The degree to which those levels are separated is called, rightfully so, the anharmonicity. And achieving high anharmonicity is a good thing in this system. So why superconducting qubits? Why are they more special than other modalities? So one is that we manufacture them, right? We use planar IC fabrication technologies, just as was used for, say, silicon and transistors, and we apply them to superconducting materials. There's a lot of compatibility that's there. And so there's a lithographic scalability right from the start. And what's illustrated here is we fabricate on 200 millimeter wafers. And you see some pictures of the qubit and also some Josephson junctions at the bottom. These are SEM pictures. There are two basic fabrication approaches that we use. One is called a subtractive approach, where you deposit metal and then etch away what you don't want, add back more dielectric, more metal, etch away what you don't want. This is closest to how transistors are manufactured today. And an example at the right is shown. So the other approach is additive. shadow evaporation, where you create some stencil-type masks that only puts the metal where you want it. And we've made qubits in both processes. And as I'll show in a moment, our best qubits are made in number 2, the shadow evaporation process, in terms of their coherence. Okay, the second reason I would say why superconducting qubits is because they're fast. So you can do nanosecond scale gate operations. And so what's shown on the right is a dual channel arbitrary waveform generator. And this arbitrary waveform generator, the way that we control the qubits is that will apply a pulse envelope, like a Gaussian, for example, to an IQ mixer. And the input to the IQ mixer is a microwave. And the microwave tone is resonant with the level separation of the qubit that you're trying to drive. And that's typically around 5 gigahertz. So this is cell phone technology is appropriate here. And whether it goes through the I channel or the Q channel, this pulse determines whether the phase goes through as is or whether it gets shifted by 90 degrees. So it's called in-phase and quadrature pulsing. And so what it looks like, we represent this on the Bloch sphere. So the Bloch sphere, or you can think of it as Poincare sphere, is a way to represent a 2-level system quantum mechanically. And so when the qubit is pointing towards the North Pole, that's state 0. And when it's pointing towards the South Pole, that's state 1. And what's illustrated in time here are different types of pulses that we generate by having this arbitrary waveform send a pulse either to the I channel or to the Q channel. So it's now approaching a Q channel. This red vector that comes out is illustrating the amplitude of the pulse. There's a pi/2 pulse which takes it to the equator of the Bloch sphere, and a second pi/2 pulse brings it back to the North Pole. So this is how we control these qubits. The last element here, which is very important, is that there's been a remarkable improvement in the qubit coherence over the past decade. And this has been a combination of materials, fabrication, and design improvements. What's plotted at the right is the coherence time, T2, as a function of the year. So the first qubit, superconducting qubit, was from the NEC group at a nanosecond, actually a little bit less than a nanosecond, in 1999. And since then, there's been a 5 orders of magnitude increase in this fundamental metric. Now, many different types of qubits are shown here. I won't go into the details about them all, but let me say that the blue dots that you see, those are contributions that we've made from Lincoln and MIT. These lower ones here, in the early years, these were made by our niobium process, and we had, and still do have, the most coherent niobium qubits in the world, but they peak out at around 300 nanoseconds. So we switched to aluminum, and these upper dots up here are the aluminum qubits. And one feature, I would say, of Lincoln and MIT is that we look at all the different types. So for example, we have a flux qubit that's got a T2 of 23 microseconds, 2D and 3D transmons that are state-of-the-art, and we even have a new capacitively shunted flux qubit, which I'll talk about, with T2 up at 90 microseconds. And the last thing I can say about superconducting qubits, which is very nice, is that they're applicable to both types of quantum computing, whether it's gate-based or quantum annealing. Okay, so let me now turn to some of the quantum engineering that we're doing. We'll start with the qubit plane. So here are the architectural layers of a quantum information processor, abstracted. And this is work by Cody Jones at HRL. What you can see is that he's represented it as 5 layers. At the bottom layer are the physical qubits, the individual elements that build up the computer. At layer 2 is passive error suppression. This is called dynamical decoupling. And it's essentially an open loop error cancellation technique, which I'll describe in a moment. And the idea is, let's make these qubits as good as possible, increase their coherence time as much as possible, reduce their gate error as much as possible, before we have to do layer 3, which is really hard, and called active quantum error correction. So this is what Peter Shor came up with in '94, which is a way to allow the computer to run fault tolerantly. Because clearly, if the coherence time is a microsecond, and I used this example earlier that it's going to take us a day to factor a large number, that's incompatible. And so quantum error correction, at least as we see today, is clearly going to be a part of any foreseeable quantum computer. And if you look at, for example, transistors in your laptops, right? What is the error rate of a transistor in a laptop? It's probably 1 part in 10 to the 15 or 1 part in 10 to the 20, right? If the computer stops working, it's usually a software error, right? And what we have is error rates now at 1 part in 10 to the 3, 1 part in 10 to the 4. And we're working really hard with materials and fab to improve that, but we're not going to make up 16 orders of magnitude. At least, maybe I shouldn't go on the record and say that. Engineers are pretty clever, but that's a big difference. And so quantum error correction is going to be an important part of making up that difference. And the way it works is that you start with these faulty qubits, and you do error mitigation, that's layer 2. And then you do error detection through the quantum error correcting codes to see if there's an error. And then you correct for it. And then you do a logical operation and correct for any errors. And then you just keep cycling this around and around. Every clock cycle, you'll do this over and over again. And the most advanced, as far as I know, demonstration of this is from the UC Santa Barbara Google group, where they've done 5-qubit and 9-qubit repetition code. This is not a fault-tolerant code, but this is a very nice demonstration along this direction. And as is suggested by this picture, they've only done a 1D chain here, but they've drawn it in the context of a 2D plane, what's called the surface code, which is this lenient code that allows us to do fault-tolerant computation. But what I'd like to talk about is some work that we've done at layers 1 and 2. And so let me start with layer 2. And this is open loop error mitigation, or dynamical decoupling. And it's, the concept is pretty straightforward. So for example, I think of it as lacrosse cradling. I don't know if you've played lacrosse before, but the idea is that you have a ball in the stick in this wicket, and if you just run with it across the ground like this, running creates noise and the ball pops out very easily. So nobody does that. What they do is they cradle it. They go like this, right, as they're running. And just by doing this, you decouple the ball from the ground, from your running. And that works most of the time until this guy in red comes up behind you and knocks it out. Of course, you're not preventing that, right? That's going to happen once in a while, but at least you've improved the situation dramatically. And so the analog here is that passive error correction is the cradling, and active error correction is going to be mitigating the defender. So we applied this technique, demonstrated it for the first time in a superconducting system, using a qubit that was a very good qubit in 2011. It's the first one to exceed 10 microseconds. But the red boxes here, what they indicate was a puzzling question. And that is that if we do a Ramsey experiment, which is shown right here, which is essentially 2 pi over 2 pulses, we take the spin and we put it on the Bloch sphere's equator, and then we let it precess. That's what the oscillations are. It will do that with a decay time of about 2.5 microseconds. That's pretty short. But if we do a spin echo, which is over here on the right, so we do the same pi over 2 pulses, but then right in the middle we put a pi pulse. And I'll show more examples of this. So the point is that just by doing that 1 pi pulse, we were able to extend the time to 23 microseconds, factor 10. So the way that we can understand this, and this is the one place in the talk where I'll have some math, is to think about what causes qubit dephasing. And so if you have your qubit, energy levels 0 and 1, they're separated by an energy E01. They're at different energies, and so these two states will accumulate phase at a different rate. So if I have a superposition, alpha 0 plus beta 1, we can write it in such a way where it looks like state 1 is accumulating a phase in time. And if it's a deterministic phase, if there's no noise, then it does so predictably ad infinitum. But if there's some noise in the system which is causing this energy level to fluctuate, this will cause dephasing. And then this is this random variable here, phi tilde. Now the phase accumulates in an exponent, so we can calculate what's the ensemble average that we expect for this phase. And it's really just a time integration of the frequency, which is energy divided by h bar. And if we assume some reasonable things like Gaussian distributed fluctuations, there are lots of sources of this noise, we can write it down in this very appealing and intuitive way. So there's an exponent, and then there's tau squared, which is the time. The first term there is the change in energy per change in whatever's causing this noise. It'll be flux noise as we turn out. We'll call it lambda here. And that quantity squared. So this is the sensitivity of the energy levels, how much the energy fluctuates for a change in this noise parameter. And then the second term is an integration of the power spectral density of this noise, which is the variance. So that's how much fluctuation you have, but weighted by this function we call here g, which is the filter function. And the filter function depends on which pulses you apply. So if you know what S is, the power spectral density, you can choose a filter function, i.e. you can choose a certain set of pulses which will shape that noise and hopefully mitigate it, or at least reduce its impact. So the filter function depends on the pulse sequence, and it windows the power spectral density. So here's an example. This is just what's called a spin echo. So we do a pi/2 pulse, the spin goes on to the equator, and then due to noise, it's going to diffuse. It goes at different rates. So I think what's simulated here is maybe 10 instances or something like this. Quasi-static noise. So for each instance, we assume a fixed level of noise, and that's what causes the precession. So you could imagine this as a loop with a magnetic field that threads the loop, and the spin is going to precess around that magnetic field. And the value of the magnetic field is changing, so the spin precesses at different rates. Sometimes it goes forward, sometimes it goes backwards. And the way that we can understand this is in the following way. So we have these 2 pi/2 pulses, and then the period of time in between is called free evolution. We're not doing anything, we're just watching the qubit. And this free evolution has a fixed energy level separation. We said the noise is quasi-static. And so it looks like a rectangle, right? If we take the Fourier transform of a rectangle, we get a sinc function. And so the filter function corresponding to doing nothing is a sinc function. And of course, I'll say that this flux noise is 1/f like. We've measured that many times. And so what you can see is doing this is one of the noisiest things that we can do, because the peak of the filter function is also at the peak of the noise. And so when we integrate it, we get a lot of noise. So the second thing we can try is to put a pi pulse in the middle. This is called a Hanako, named after Erwin Hahn in the 50s, who did it in NMR first. And as you can see, it refocuses the noise very efficiently. And so what's happening is that the first period, there's a rectangle here, tau/2, comes in with a particular sign, let's call it plus sign. But after the pi pulse will flip everything upside down. So now the second interval comes in with a minus sign, and if we take the Fourier transform of these two rectangles with a plus sign and a minus sign, we get this green filter function. And now it's moved out to a higher frequency, and so this reduces the effective noise seen by the qubit. And the intuition of why it moves to a higher frequency, while these time durations are a little bit smaller between the various pulses, and so that goes to a higher frequency. And so if you add more pulses, the situation indeed gets better. And so here we have an example of 2 pulses. The duration of time becomes smaller and smaller, and so the filter function, now shown in red, goes to higher and higher frequency. And the degree to which this is improving the situation gets better and better. Of course, there's no free lunch here. I had to apply some pulses to do it, so it took some resources. But a factor 10 is a big factor. So we demonstrated this back in 2010, 2011, and showed that we could, in fact, take a qubit that's intrinsically biased at a very noisy point and improve its decay time by about a factor 50. Went from 300 nanoseconds or so, and increased dramatically. And so approached the limit, which is twice T1. And the reason that's a limit, if you're on the equator of the Bloch sphere, of course, you can dephase on that equator, but also you could just relax off of it, right? And so we know that at some level, T1 is always going to be a limiting factor. And then that needs to be corrected by layer 3, quantum error correction. Now, the second thing we can do is let's make a better qubit to begin with, right? Let's increase T1 as much as possible so that I can do these dynamical decoupling pulses and hopefully achieve twice T1, and I want to move T1 up as high as possible. And so we did that recently with the Flux qubit, driven primarily because it's a good qubit for both gate-based and annealing. And so the question is, what can you do to improve T1 in a Flux qubit? Well, we know that design and materials and fabrication can all impact the T1, and the way that it does so is through Fermi's golden rule. So Fermi's golden rule is essentially the rate of decay, 1 over the T1 time, and it's proportional to 2 terms. The first one is essentially a matrix element X. You can think of this as a generalized dipole operator that causes the transitions between the excited state and ground state. And so we borrowed an idea from the transmon community. That's another type of superconducting qubit where they added a large shunt capacitor. And so we asked the question, with some help from people who proposed this idea, listed at the bottom, what happens if you do this? And it turns out that it helps. It reduces the sensitivity to charge noise, and it also reduces the sensitivity to stray capacitance. So if you add a big capacitor to the Flux qubit, which intrinsically has a very small capacitor, and you have some small stray, you just don't see the stray anymore. You see the big capacitor, right? The second thing we did is we reduced the circulating current in the qubit loop. And this reduces sensitivity to flux noise, so that's a good thing. It also slightly increases sensitivity to charge noise, so it counters a bit adding the C-shunt, but overall it's a net win. So that's on the design side. On the other side is the power spectral density. What can we do to make the noise environment have a lower noise? And so what we can do is improve the capacitor film quality. So we improved how we fab it, how we grow it. And so this increases the capacitor Q, if you will, and reduces its noise. And the other thing we can do is optimize the geometry of the capacitor. And what that means is, of course, the capacitor has some electric fields that go from one plate to the other. And there's some distribution of defects there that are causing this noise. Of course, we try to reduce the defects as much as possible, but whatever's left, right, we try to make sure that the electric field samples them all equally, that there's no high intensity regions of electric field, because if it is, then those defects participate much more strongly. And so this is the qubit that we came up with. So it's a flux qubit with a square capacitor. There's qubit A and qubit B that are shown, and a zoom in of qubit A shows the capacitor. So these are two plates. The electric field goes from one to the other, and in between is the qubit, and then that's the zoom in shown here. It's a 3-junction loop. The junction on the left is smaller than the other two that are on the right. Now, we could perform spectroscopy, find out what the energy levels are of these two qubits, and they're shown on the right. Here's qubit A and qubit B. And one interesting fact here is that this qubit has 3 to 5 times the anharmonicity of a transmon, and that's a good thing. We talked about that earlier, is the 0-1 transition versus the 1-2 transition. And the more different that is, the higher the anharmonicity, the more useful it is for quantum computing. And the T1 and T2 times here are very good. So T1 for these two qubits, 44 and 55 microseconds. The T2 measurements, I only show one here, but they're similar. And so the T2 with an echo is about 90 microseconds. This isn't a planar device. So it's a very good T2 time. And if you ask without the echo, what was it? It's about T1. It's about 40 to 50 microseconds. And so I believe these are state-of-the-art qubits. And they're in a planar geometry, which is, again, leads to lithographic scalability. I'll just mention in passing that we've developed models for the noise which allow us to predict what the value of T1 should be across a very wide range of designs. So by changing the design, this is not fabrication variation, just the opposite. By varying the design, we were able to create qubits that had a low T1, around half a microsecond, all the way up to, say, 50 microseconds. And these are the data points that are shown here. And this is measured versus predicted T1. So all of those points should fall on the dashed line, and more or less they do with the noise model. Single noise model that we have works across all of these qubits. So this was, for us, an accomplishment. And in fact, it indicates that our fabrication is pretty good. It's reproducible. Because we pick a design, we make it, and it behaves the way that it should. So the model works and the fabrication works. So in the last few minutes here, let me talk about engineering of the control and the readout plane. So of course, the way we do it today is we have room temperature control electronics, and these are some electronics that we've built at Lincoln Laboratory. An FPGA card and mixed signal cards and backplanes and dual channel AWG. It's essentially a D to A converter and A to D converter, and a way for them to talk to each other and to do feedback. Eventually, we would like to make this cold, and we've been working on this for several years now. And what I can say at this point is that we've used cryogenic CMOS to facilitate measurements of Josephson junctions. So what that means is that what's shown here in the upper left is a probe where we use cryogenic CMOS to switch between different devices that we're trying to measure. And so there are 14 chips and I think roughly 12 devices per chip. And we only have 4 wires that go down to make the measurement. And the other wires that go down are simply telling the CMOS where to route those wires. Now that may sound very simple, and it is, but we did it at cold temperatures. In fact, we even did it in a dilution refrigerator of 20 millikelvin. And so only 24 wires could measure 151 devices. Okay, and so I think that without saying it, I think we can imagine how that could be useful if you're trying to control a quantum computer. And what's shown on the right is an expanded version of this in a dilution refrigerator where it's not just, well, let me say it's 8 of those in parallel. So, oh, and here's some results. So we test, for example, Josephson junctions with this, and we can get IV traces. Again, in a dilution refrigerator, the temperature remains less than 100 millikelvin, even in the presence of this cryogenic CMOS. So this is an active area of research for us now. I unfortunately can't talk much more about it than that. Now, another type of control logic that we're working on is called single flux quantum, or SFQ electronics. And this is it's classical. It's digital superconducting electronics. It's a flux shuttle logic. So you have a loop, and the loop is interrupted by a Josephson junction, shown here. And then you can think of that junction as a valve. The valve lets in an amount of magnetic flux, it lets out an amount of magnetic flux. And the presence or absence of that magnetic flux is the digital 0 or 1. And what's shown at the bottom is just a simple schematic of a D flip-flop. What makes this very interesting is that the switching energy is extremely low and conducive to using in a dilution refrigerator. So what's plotted is the energy versus the speed. And what you can see is that these SFQ, indicated in the green here, these types of devices are much lower energy than competing technologies. Now, CMOS can be made better by cryo-CMOS, indicated by the blue arrow, but it doesn't quite reach SFQ. And so the applications here are interesting. It's also high-performance computing, but also cryogenic control electronics. And we have an very active research area here. Showing a side cut of an 8-layer RSFQ wafer. Okay, so we make a wafer, we grow 8 wiring layers, and there's junctions in there and resistors, all the things you need to build circuits. This is the most advanced process in the world, as far as I know. We've demonstrated circuits that have 70,000 junctions, operating at high speeds, very important. And the yield presently is limited by the designs. And the fact is, in the past, people haven't had fabrication facilities able to make these types of devices, so we haven't been able to turn the crank too many times on the designs. But now we can. And so this is a very exciting result for us. The densities we're achieving here are 1 to 2 million junctions per square centimeter. Now, using that same process, we can make low noise amplifiers. These are Josephson-based traveling wave parametric amplifiers. Amplifiers which have decent gain, and the amount of noise they add, it's at the quantum limit. It's limited by the rules of quantum mechanics. So I just have a few pictures. On the left here is a 5 by 5 millimeter chip. If we zoom into the red square, you can see a transmission line. I'll show this in a moment. And then there's some resonators, inductors, and capacitors to do what's called phase matching. But this is what it is, essentially. It's a telegraph's equation. If you look at a telegraph line in the upper left, you can approximate a 50 ohm impedance line by elements, inductors and capacitor, inductor, capacitor, repeated over and over. And in this case, again, the Josephson junction is a nonlinear inductor, which provides the nonlinearity for this amplifier. So what's nice is that this is a 50 ohm impedance matched device, but it provides gain. And it does so by what's called a chi-3 nonlinearity. It means that you have a pump and a signal photon that come in, and what comes out is an amplified signal, 2 photons. And it's a broadband device. It's not resonant. It's 50 ohm matched, right? So we can actually think about frequency multiplexing many, many qubits together, sending them to the same amplifier, and then, demultiplexing. So just to show some numbers, the gain is greater than 20 dB over about 4.5 gigahertz of bandwidth, and this is incredible. A year or two ago, the best you could do was these kinds of gains over maybe 10 or 20 megahertz. And in terms of its noise temperature, it has a noise temperature of 0.4 Kelvin. And to give an idea, that's a quantum efficiency of about 80%, where 100% would be at the limit that quantum mechanics allows. So these are very good amplifiers, and we hopefully will get it published very soon. I should mention, I think I had it on the previous, Ted White in the Santa Barbara group has also made an amplifier of this type now. And so finally, our concept, of course, is to integrate these. And so we have a qubit chip that we will flip chip onto, so that's the qubit plane, and that gets flip chipped onto the control and readout plane using things like this superconducting multi-chip module, coaxial through silicon vias, et cetera. And these are all things that we're working on. So the last point I'd like to make is we've succeeded in flip chipping and measuring qubits. And so what's shown in number 1 is the qubit side of this, the qubit plane. And it has a capacitively shunted flux qubit on it. And number 2 is the other side, the control plane. And you flip chip it over and connect it with indium bumps. So this is what it looks like. So there's 2 chips here. One's 5 by 5 millimeters. The other's 5 by 2.5 millimeters. And so you flip it over. It's really this easy. Yeah, you flip it over and you push it down. And indium bumps make electrical contact. And so you can pass signals between the 2 planes as you need to. This is what it looks like when they're packaged. And these are preliminary results, but let me say that we've measured several qubits now, and they have T1s between 10 and 15 microseconds. So not our best T1 times, but they're pretty good. Doing this process, we found, didn't harm the T1 dramatically. And in fact, the next step is to assess what we can do to bring that T1 back up. And so let me conclude not by just repeating everything I just said, but by saying, look, the coming decade is now. The past decade was all about trying to take this laboratory curiosity and make it better. And this coming decade now is going to be about engineering quantum systems. Thank you very much.
So it was very interesting to see your 90 microsecond flux qubit, but you're coupling with the true resonators, right? That's how you couple the qubit. So this would be for the gate model, I assume? Or
yeah, so this was, you're right, that what we demonstrated was 2 qubits coupled via a resonator, but that in fact is not the way that we want to couple 2 qubits together, either for gate-based or for quantum annealing. And the way that we want to do this is to have a separate entity, which we would call a coupler, between the 2 qubits. And that coupler would allow tunable coupling. You could turn it on or turn it off.
Yeah, because
magnetic or ferromagnetic.
There was a bigger space. You put them big loop, that's your capacitor. And I was wondering, how do you want to directly couple them? But you say you have a way.
Yeah, so we've been thinking about this. The geometry of the squares, prohibits entry, let's say. But once you go to a 3-dimensional world, right, you don't necessarily need to come in from the sides.
Okay. Thank you.
On the level of the architecture for an annealer, one of the key figures of merit there is, of course, the degree of connectivity of the graphs that connect the qubits. Could you maybe address this a little bit? What you think may be achievable in terms of how high of a degree in the connectivity graph we could get?
So I can tell you what we would like to do. And at this point, this is all just ball and stick diagrams. But we think we have a way to get a connectivity of maybe 1 to 40 or 1 to 50. But that has to be demonstrated. At this point, it's just a drawing on a piece of paper. So, but if we could get something like that, I think that would be great for a first test bed. Yeah. And we'll see how close we can get.
So there is also another requirement for a quantum annealer that you can embed interesting computational problem. Is that like a k-local interactions? Do you have any idea how to do it, like a 3-4 local interaction?
Yeah. So we have some ideas along these lines, but we haven't been able to demonstrate it yet. So we're in the process of trying to demonstrate a 3rd order or 3-body or 4-body interaction. I don't know if it's going to work. So maybe in 6 months we can say, yeah, it worked or it didn't work.
I was wondering how many qubits you think it would be possible to build within a decade in both the gate model and the quantum annealing model. You're saying now is that in this decade is going to be engineering of these lab curiosities and taking them to an industrial level.
Yes.
So I was wondering, if you were to dream a number of how many qubits do you think we will see in a device, in a working device, within the next decade?
Yeah, it's always so dangerous to answer these questions. Let me answer with a factual statement. Okay, so we fabricate on 200 millimeter wafers. Okay, And on a 200 millimeter wafer, we're achieving 1 to 2 million junctions per square centimeter. And that's with very, what I would say, lazy levels of integration. So I don't think that the challenge is going to be, I think the lithographic scalability is straightforward. What's really challenging, of course, is going to be maintaining coherence amongst those qubits and maintaining controllability and also the readout of those qubits. And there, okay, there's much less visibility in what we can do in the next decade. But I'm optimistic because we've made so much progress over the past decade in terms of coherence, and also, you know, this recent work that we've done with flip chip and 3D integration and through substrate, through silicon vias. So I don't know the answer, but it'll be a big number.
This I found quite exciting that you have the flip chip technique already working, and that you had took the first T1, T2 time measurements. Actually, I think I only saw the T1 time. You have T2 measurements already too?
They're similar, in fact. I didn't show them, but we do now have T2 times measured, and it's on the order of T1. So, yeah, and in fact, the echo time is twice T1. And I think that because T1 came down a little bit, we can get an echo time to be twice T1 with no problem. And in our best qubits, you know, T1 is maybe 50 microseconds, and we get close to an echo time of 90 microseconds, just shy of twice T1. But in these qubits where we flip chip them, it's really twice T1.
Our AV people just said that there are some questions from people on the other side of the video conferencing system. So if there are some questions, they will face you in, so you can ask. Oh, I see Eddie there on the screen.
Yeah, I have a question. So how general an interaction can you get between qubits?
So
you have more than sigma z, and and sigma x's. How general can you be?
Yeah, so the idea or the scheme that we have now that we're trying to demonstrate would be able to do an arbitrary interaction between two qubits, where you can think of an angle that we're tuning between sigma x, and sigma z. So we can, you know, on paper we can do it, and I think now we need to demonstrate it.
Thank you.
Yeah, so you can turn on those with arbitrary strengths, you know, between the two.
Well, thank you for a very
thank you very much.
talk.
Appreciate it.